So, afternoon everyone. Say everyone, there's only 4 of you out there now. So that's, numbers are getting up. So we're into the last week before Easter now. So this will be the last week that I'll be lecturing to you. I can hear the cheers from here. So, oh, everyone's joining now, that's good then. Okay, so we've got 2 more topics to cover, loosely called data converters. So these are analog to digital and digital to analog. So I'm sure you've done a little bit of this already, but we'll be again starting from nothing, whizzing through, and we'll end up with looking at something called sigma delta converters, which are some quite nifty little ideas, and it allows us to introduce the idea of noise and how to get rid of it, or at least how to reduce it. And we'll look at other types of A to D converter on the way. Yes, right, I always get around the wrong way. A to D, D to A. So this is analog to digital, so this is going into our digital system for processing. Okay. Right, so a little bit of background on A to D systems. Normally, everything we've been looking at, sensors, everything else, signals that we're interested in tend to be related to the physical world at some point in the process, and we turn them into electrical signals, typically analog, and we've looked at various processing techniques in terms of amplifiers and filters and things like that to convert our signals into the electrical world, and then convert them in the electrical world into a form that we want, in terms of the gain and the range and the bandwidth and all this kind of stuff. And then quite often we'd like to get these into the digital world, because we can apply all kinds of interesting digital effects to these things. We can do sums, calculations, display them, transmit the data, and so digital becomes very important. So analog signals are analogous. They've got continuous change in amplitude, and they continuously change in time as well. And digital signals are discrete in amplitude and time. So digital ones will have a certain amplitude within a fixed range at a certain time, and then that won't change until the next time step comes along. So to get from analog to digital, there are a couple of steps we have to take. We have to first of all sample the analog signal to make it time discrete. So we grab a sample of it and hold it, and then a bit of time later we'll grab another sample of it and hold that, and then when we've grabbed it and held it, we would digitize it, and this will make the amplitude of the signal discrete. So we do time discrete, and then we do amplitude discrete, and discrete means there are defined steps. It's not continuous anymore, and this leads us to the ideas of resolution and size of bits and things like that, which we'll talk about. And there are many, as always, different ideas and techniques that can be applied to take an analog signal and turn it into a digital signal, and back the other way as well, as we'll look at the end of the week. And each of the techniques always trade off something. So there's a trade-off between bandwidth, so what's the fastest signal you can accurately grab hold of, the accuracy as well, so how many bits we're going to have into it. These always lead to more complexity of circuit if you want both of these at the same time. That leads to cost. Something that also might be interesting to you is power consumption, and we've last lecture we looked at the issues of power consumption, dissipation within devices. Things get hot and can fail, or things can drift around with temperature. So there are lots of different techniques, and there are lots of trade-offs between it, and we'll have a look at some of those trade-offs as we go forward as well. So we need to be able to sample a signal at the right time and get the spacings right. So in principle this is straightforward. We need just to get enough samples to allow us to describe our signal. Ideally we won't want to go mad, and we won't want too many samples, because that just makes life easy for us. So we have to understand where's the limit, what's the minimum number of samples that we can get away with of our signal and still be able to say that it is a representation of our signal. And hopefully many of you will be familiar with this idea of the Nyquist frequency, which says briefly that you need a minimum of 2 samples per period of the highest frequency we want to sample. And if we are not inside this range, we end up with a feature called aliasing. And that's not a good thing, and we'll look a little bit about the nature of aliasing and where it really comes from and how we can get rid of it, and what we can do in principle, but what we actually have to do in practice as well. So the basic idea of sampling is to grab the value of the analog signal at a particular instant in time. So here's our analog signal, continuously changing in time, continuously changing in amplitude. It's all joined up, no straight lines involved here. And we represent that by x of t, so t implies time continuous signal. And we're going to sample this at t sub s at various time steps where the gap between ts's is ts and is constant. And that results in a sampled signal xs of t. So we've got xs of t here, which is these points taken at discrete points in the waveform. So we do that by sort of convolving it really with a time point, and these are we're sampling effectively mathematically with a set of points that are infinite, have an area of 1, and are infinitely thin. And then if we join these two together, we end up, or multiply these together, we end up with infinitely thin spikes that have the height of the original waveform. And this is plainly impractical, I would suggest. First of all, getting spikes that are infinitely thin and sampling at this point, there's always going to be some variation or some finite value of the width of this thing. So we have to go a little bit further than that, and we end up, to cut a long story short, we end up doing something called a sample and hold. So if we take our input signal, which is continuous, and we have to sample it at fixed points, ideally these are the points that we would like to sample it at, but we can't have these infinitely thin spikes. So what we actually do is we just sample it at that point, and then we hold it until the next point, and then it gets sampled again. Then we hold it, and then it gets sampled again, then hold it, sample it again. And this now gives us a set of sort of a histogram, if you like, and then the maths of histograms are a little bit easier to cope with. And importantly, the system now has the time between the samples to digitize the signal, because remember, this is only digitizing it in terms of time. We need to now digitize it in terms of amplitude as well, and so now we've got this period of time to actually do some processing and work out what the amplitude actually is of this signal. And the signal is being held for us, so we can keep referring back to it if we want to, which various techniques like to do. So it's subtle, it's sort of obvious, but it needs to be stated. And this is where it starts to get a bit more interesting, because then what we need is something called a sample and hold circuit. And in its simplest form, this can be a capacitor and a switch. So we close the switch, the capacitor charges up to V in. We then open the switch, and V in is now held on this capacitor. But this is the ideal case, and this assumes that no current goes into V out, and no current leaks through here as well. It also assumes that when we close this switch, that this capacitor can charge up quickly enough to be able to follow a changing signal at this input here. So this implies that the output impedance seen at V in, so the resistor here, is actually quite low, so that the time constant between the input impedance here and here is fast, so that this can charge up really quickly or discharge really quickly and follow the signal. Likewise, we also assume that the impedance looking out of here into the proper converter itself is going to be very, very high, so that once we've closed this switch, any voltage on here is maintained and no charge leaks off. We run into problems because, although it's a simple idea, the switch causes us the grief here. the input impedances as well, but we can sort of work around those maybe, because we can think, okay, we understand now the importance of high output impedances and low input impedances. The switch itself is probably going to be a transistor or something like that. That in itself can introduce its own issues, because as it switches, as it charges up, there's going to be little capacitances within the switch itself, because there's, even a transistor, we have a diffusion layer and junction potentials which need to be charged up. So there's the potential to have an error introduced by this switch as it injects charge into this capacitor. As it opens and closes, it has to charge and discharge itself. And we touched upon this briefly with the switch capacitance stuff that we did last week. And in fact, these switches can be some of the integrated switch capacitance switches. So some of those IC building blocks that we talked about last week, I forget the name of it, but there's a chip that's just a bunch of very high quality switches. So this switch could be one of those switch capacitance switches, and it would do a reasonably good job. But like all these things are characterized because people who design switches for a living like to be able to measure them and tell us what's a good one and what isn't. And so this is the sort of trace you might get of someone who's been looking at a sample and hold switch, and they can define this thing called droop, which is the interesting thing. First of all, there's a small error. This is the signal it's trying to track. So there might be some slight errors in the track voltage, depending on how fast the signals are moving. And then when you've closed the switch, you end up with this thing called droop, where the charge in here is balancing itself or slightly leaking out, or there's a resistance across here that's starting to leak out. And the amount of droop on the switch, or the sample and hold, is indicative of its quality. And the other thing you're interested in, how fast it can actually track. And you can see the time constant sort of emphasized in this kind of diagram here. So you can see if you switch it quick enough, it won't be able to follow these waveforms. So there's lots of, even in just designing a switch, there are lots of parameters that need to be looked at and thought about if you're going to do it properly. And again, you can have a whole career in switch design if you really wanted to. Okay, but some basic ideas for how we might reduce these problems. So building on what we know about buffers and amplifiers and things like that, this is just a buffer. And we know that buffers have very high input impedance because we're going straight into the op-amp, and it will do whatever it can to maintain this voltage difference here at being 0, which means that V minus would have to become V plus, and the output voltage then becomes V1. So it's sort of followed it all around, so that's a buffer. There'll be small errors, offset voltages and things inside this, depending on how good the op-amp is, so we understand that from early on in the course now. We've got a switch that will allow us to sample the voltage. We then charge that onto a capacitor, so we want a low leakage quality capacitance there. And then we wanted a very high output impedance here, so we put another buffer on. And we know that the output impedance of the op-amp here is very low, so that's good. We can charge the capacitor up easily, so that's sort of solved our problem. The problem we do have with this is that both of these op-amps will have offset voltages associated with them, because we never get 0 out for 0 in. It might only be very small, but we're still going to get it. We've got 2 of them, so there could be some issues with that. So people will say, okay, well let's try and get rid of that. Let's just put one feedback loop around this. So here's an example sample and hold circuit that I took from a data sheet. And here we've got a single loop around the outside of it. So we've joined up. We haven't got this loop here anymore. We've just joined the whole thing up. And so the output now, any offsets in here should be absorbed into this op-amp here, so they should be compensated through this buffering arrangement here. So we should now get a very good output. Certainly we've reduced the dependence on the independence of these offset voltages anyway. The problem we run into now, of course, is when we open the switch, we've opened the loop, because if you imagine there was a loop here, let's put a pen on here. If we've got a single loop around here now, all the way around, and we break the loop here, then what's going to try to happen is that this op-amp will try to maintain 0 volts between its inputs which would normally be a nice closed loop system. It's now open, so whatever it does here, it's going to run into grief if this signal moves around. And then when you close the switch, there's going to be a disjoint between the voltages, and there's going to be a big surge, because normally this will have gone to one rail or the other. So these designers put a couple of diodes in here to limit the amount of movement, that when this is open, that this voltage can only move by a maximum of 0.7 of a volt in either direction, so it's been clamped. And then when you close the switch again, this output, instead of going to one rail or the other, has only gone to about 0.7 of a volt, so it's much quicker to it hasn't got to cover as much ground to recharge this switch up. So you can see that so we're compromising this straight away in terms of its speed, but we've maintained a little bit of accuracy compared with this one. But these would work, and you can replace this switch with one of those switch capacitance ones, and it will work quite nicely with these two diodes in place here. So even the idea of a simple sample and hold suddenly becomes reasonably complicated, and this is a relatively simple one, and there are lots of other ideas with multiple switches and things for charge balance and all kinds of stuff that you can make this really complicated if you want to. And these become really important when we start to look at digital to analog converters. We don't want any errors introduced with those either, so we'll revisit this again when we look at this at the end of the week. So what rate do we need to sample at? And this is not a simple question to answer either, so you're getting the idea that there aren't simple answers to these questions. It's all a compromise. We know that there's a limit below which you cannot sample and keep all the information needed, and even that's not strictly speaking true. So in general terms, then, we can get this intuitively by looking at, for example, the waveform below. So here's the red line. If we sample this at these indicated points here, then we'd have no trouble intuitively in reconstructing the red line. But if the signal was following the blue line or even the green line, and we sampled at the same points, we haven't got enough information to be able to rebuild the blue or the green ones. So we would have to just resample, or say that we had this waveform here. And this is an indication of aliasing, because we're disobeying the Nyquist thing, and we're not sampling at enough points within the waveforms. The bit about having two samples per waveform is the important bit, though, because what that means is that if we wanted to grab this green one, we'd have to have a lot more sample points, obviously. But if we're only interested in the red one and the green one is like superimposed on top of it, is like noise or something like that, or another signal that we're not interested in, then we can actually filter this whole waveform through one of the filters that we looked at earlier in the course, get rid of the high frequency stuff, and that allows us to then be guaranteed that anything we're trying to digitize after that point is below a certain frequency. It's below the cutoff frequency of the filter, and therefore we can then predict what the Nyquist rate needs to be and work within that, and that's called an anti-aliasing filter. So the sample rate becomes intrinsically linked to the bandwidth of the input signal you're trying to sample, and if your input signal is not band limited in the real world, and some of them are, like normally acoustic signals are pretty much going to be band limited to less than 50 kilohertz, because sound doesn't travel very fast or very well above 50 kilohertz, so most of the stuff you'll be listening to is well below 50 kilohertz, and even the microphone that's transducing it will have a bandwidth probably less than 20 kilohertz. And so you don't necessarily need an anti-aliasing filter for audio systems, because the microphone, for example, is the filter. It doesn't respond to higher frequencies. So as long as you sample at the bandwidth of the microphone, or twice the bandwidth of the microphone, you don't need an anti-aliasing filter. But that can't be true for lots of other systems, such as communication systems and things. So you have to think about anti-aliasing, and the filters that we've looked at are very important for that. And the cutoff frequency of the filter and the response to the filter is very much dependent on the sampling rate that you wish to get away with. So just to quickly look at what happens if we do oversampling. It's easy to reconstruct these, and here we have got, so this is 10 samples per wavelength, 8 samples per wavelength, I think it is, count them anyway. And then if we sample at 2 samples per cycle, which some people say is the Nyquist limit, you can see that if we happen to get it right here, we can reconstruct the signal. But if we sample at a different point in the waveform, then it could be a choice of either of these two sine waves, and in fact a whole bunch of other ones in between. So, and if you happen to sample at the Nyquist frequency, but at the wrong time in the sine wave, at zero phase, at this point here, and this point here, and this point here, and this point here, you'd be reconstructing nothing if you're not careful, because you're sampling, you're seeing nothing. So 2 samples per cycle isn't enough. You need a little bit more at the very least, and the reality is you're not going to really get close to that. And if you undersample, so we're sampling what we'll call the blue wave, but the grey wave if you like, the fast one, at less than 2 samples per wavelength, then when you come to reconstruct it, you'll reconstruct the green waveform, which is wrong. So this is another example of why you need to band limit your signal and get it right. Right, so if we look at it, that's in the time domain. If we start to look at things in the frequency domain, maybe that helps us visualize what's going on as well in a bit more detail. So if we took a signal that had a bandwidth of omega n, so this is the width, if you like, of the bandwidth of the signal we're interested in. So this one is inherently band limited to this point here. So we've got lots of energy at low frequencies, less energy at high frequencies, and then it cuts off. So that's the envelope of our frequency response, and this is frequency increasing. So that's our input signal, the spectrum of our input signal. If we then sample at the Nyquist frequency, we end up by multiplying the frequency information up onto the harmonics and surrounding the Nyquist frequency. So it's a form of modulation really, and so we would expect it to be up here somewhere, but also we get lots of harmonics, and these go forever as well. And we need enough room to be able to move our band limited bandwidth, if you like, up the spectrum without it overlapping. If we don't move it far enough, we end up in this sort of situation here. So we've sampled it at the wrong frequency. We've only moved it so that we've got an overlap at this point here, and this is aliasing. And any kind of aliasing like this gives us errors in our signal, because when we eventually take the one section of this that we're interested in, we find it's been polluted by the neighbouring ones. So if you can view it as the images are folded onto the baseband and cannot now be separated, because this bit of the triangle here, which was here, is now inside our baseband, and that becomes a problem. We can't take it out, because as far as the system's concerned, now that's part of the signal. Can't separate that. That's in there now. Can't get rid of it. So we need to space these out a bit. So if you sampled at a higher frequency than Nyquist, these would spread out a lot more, and we'd get gaps between the bases of these triangles, and that's a good thing, because that gives us some room to actually filter. So just a few words of warning there. It's never quite as simple as operating at Nyquist. It becomes virtually impossible to operate exactly at the Nyquist frequency. Never say never though, because this requires a brick wall filter to ensure no aliasing. That's frequency. So the frequency response that we need to get to separate that out looks like that. That's a brick wall filter. Yeah. So remember what our second order filter looked like? It would have gone like that and then dropped away. And if we did that here, we'd end up with all this allowed through. It'd been attenuated a bit, but there'll still be some in there, and that will be aliasing, reduced aliasing, but still aliasing. So we have to up the order of the filter to do that. If we'd actually spread it out a bit more, so we'd sampled up here somewhere, now you see we can get away with probably a second order filter. because we've got room to play with. We don't need such a sharp filter anymore. Right, so that's part of the problem. The other problem is that we might not even know where our Nyquist frequency is. So if we're monitoring power lines, for example, if a power line is operating at 50 Hertz, then our Nyquist frequency for the fundamental is 100 Hertz. But if we're looking for errors in our monitoring system, or we're looking for errors in the cables that our monitoring system wants to see, then maybe there's a lot more information looking at harmonics, because that's where distortion comes from. If you think back to the definition of total harmonic distortion we did last week, we're interested in the power in the harmonics compared with the power in the fundamental, and the power line going wrong is likely to lead to distortion, which is likely to lead to power in the harmonics. So we might need to sample some harmonics, and if we do that, then how high do we need to go? The Nyquist frequency of the fundamental is no good to us anymore, because we'll just see 50 Hertz. So we need to go higher in frequency, and deciding where we need to be becomes a system design problem that we have to be aware of. So to get information up to 250 Hertz, we would need a 500 Hertz or more sampling system. To make, 500 gives us this cutoff. More will give us this cutoff. So we also then have to worry about the quality of our filter as well, if we're looking at the harmonics. So it's never straightforward. And once we've got the representation of our sample, we need to then turn it into an amplitude or a number, turn the amplitude into a number. And this introduces its own issues as well. Resolution, linearity and noise are the main ones that we're going to be interested in. So resolution, hopefully we've got some idea of resolution. It's linked to the number of discrete levels that we can sample at. So we've got a 3-bit system, the blue line here, showing a chunky representation of the sine wave, and a 16-bit resolution one. It looks like a continuous sine wave, but if you zoomed in, you'd see that it was it's still got some coarseness to it, but not a great deal, obviously. So the resolution, the higher the resolution, the better the representation of the original signal, which is all good. And then we start to get to some issues of, well, how do we define what the maximum amplitude of this thing is? And the next few slides will describe this in a bit more detail, so I'm just going to scan over that at the moment. So if we'd had a 3-bit system, we would get 2 raised to the power of 3, that's E exponential, which gives 8 levels, including 0. And on the previous slide we saw that gave what we could argue is a fair representation of our waveform. In fact, it's higher resolution than a 3-bit resolution. Yeah, that's okay. I was going to say it's higher than video systems, but I think video systems is usually 6 bits now, at least. So that's not true. So what we can see is there is an issue in defining the maximum input value that can be digitized. So 3-bit converter, we can see the output code against a fraction of the maximum scale voltage. We can refine this a bit further by defining our notional maximum scale as Vref, which is the reference voltage to compare to. So here are the levels that we've got. We can go from 000 to 111, and we've divided them equally here. And even this division becomes a bit of an issue in its own right. And we get up to here, and so we don't actually get, if we count these, we've got we've got up to 111. If we wanted to get all the way up to a maximum voltage of 8/8, we'd need another bit to make it 1 0 0 0 0 0 1 and 3 noughts up here. So there is an issue, it's only a small issue, between what is normally termed Vref, the reference voltage that you're measuring against, and the maximum voltage that you can actually digitize in your system. And we'll come back to that in a minute. But what we've also got is a quantization error. So the actual voltage that goes in here might be somewhere between these two values, and the system, sorry, in here somewhere, and the system has to decide whether it's this level or this level. And if the signal was somewhere in between, then there'd be an error. And this is a measure of what's called the quantization error as the input value is going up. Here, this continuous, if we put a continuous signal in here that was increasing in amplitude up here, this is the amount of error that you get compared with the best level to be associated with for that particular signal. Right, and so the graph shows that in the case of a 3-bit converter with this kind of scaling, we can sensibly resolve up to 7/8 of VREF. 8/8 of VREF would require the other bit. We can't get that high. We'll look at that again. The other graph showed the quantization error. So that's an interesting concept which will keep coming back. So you need to get an idea in your head of what quantization error means. And we define that in terms of something called the least significant bit, the LSB. And defining the LSB is like saying what's the minimum change in input voltage that can be resolved? What's the voltage gap between two levels here? And that will be referred to as the value of the least significant bit. So it's the smallest thing that you can relate to. So by looking at this typical graph here, you can see that 7 changes in level gets us to 7/8 of VREF. So 8 changes gets us to 8/8 of VREF. So therefore the LSB, least significant bit, is given to us by VREF, which is a maximum or a reference voltage that we're comparing against, divided by 2 raised to the power of n, where n is the number of bits that we've got here. So this is a simple definition. The reference voltage divided by 2 to how many bits you've got. So it's VREF. But we also note that in our 3-bit system, the maximum number that can be represented is 111 in binary, because if we go any higher than that, we need another bit, and that's actually 7 in decimal. So the maximum voltage that can be digitized is not VREF, which is our reference voltage we compared against, because that would require this extra bit to make it 10000. But it's actually going to be VREF minus 0.5 of an LSB. And so if we do the whole graph to full scale, to VREF here, you can see that 1000 will be here. And that will be our full stage, but we can't get there because we can only represent 3 bits in our system. So we run out of steam at this point, can't go any higher. So any signal in this range coming into the system is digitized to 1111, even though, strictly speaking, we should really be, anything in this bit here should be digitized to this higher level. So we end up with an issue in terms of the definitions of this. So strictly speaking, it's only this bit that we have a problem with. But you might find if you look in textbooks and things that it says that the maximum you can get is VREF minus 1 LSB. I don't know quite why. Certain cases is to do with where we've made this decision point here, because we could make this decision point here if we wanted to, or anywhere in between, and that would shift this decision staircase, if you like, either to the left or the right. But that just sort of hides the problem somewhere else. So in terms of the maximum voltage that can be digitized rather than VREF, V in max, maximum useful voltage you can put in, is going to be VREF over 2n minus 1 over 2n. That's recognizing that we're missing this bit here. And you can rearrange that to give us, by the previous definition of LSB, to give us a new value of LSB in terms of V in max is 2n minus 1. So there are 2 definitions of LSB, which are the same as long as we're consistent. It can be VREF, which is an internal reference voltage within the converter, divided by 2 to the n, or it could be, if it's defined in terms of V in max, the maximum useful voltage you can apply to this system, V in max 2n minus 1. So you just got to be a bit mindful when reading data sheets as to which they're using as their definitions and why. Okay. So, for example, if 111 corresponds to a maximum of 7 volts of input, each bit of resolution corresponds to V in max over 2n to the minus 1, which, if you put the numbers in, brings you out at the LSB of 1 volt. Although there are 8 discrete levels for 3-bit resolution, so 7 volts is the maximum you can put in, and 1 volt is the resolution that you can get out of it. So in that case, you need, if it's using VREF as the basis for the comparisons, straightforwardly anyway, then LSB, which we know is 1 volt is Vref over 2 to the n. That tells us that we need to define a Vref of 8 volts in this system if we're free to define what Vref is. Quite often Vref is defined by the A to D converter, so then you have to go back from Vref to find out what the LSB is, and also to then calculate what Vn max is for your system, maximum dynamic range. So there's a little bit of subtlety here. Of course, it's not really a problem, because as n starts to get big, the difference between Vref and Vmax, if you like, or the difference of one level, is so small it's really not worth getting excited about. So it's a problem in smaller systems. But if you, as I alluded to earlier, if you move the sort of decision staircase over to the right a little bit, so that instead of deciding here, it decides here, then you can actually put Vref in and get it out. But the problem there becomes that if you start to make a double-sided system, this is good for a single-sided system. For a double-sided system, where the electricity goes this way, then you find that the decision point, first decision point, becomes here, and so on. And what you end up then with is a double width dead zone at 0. Whereas if you move the staircase over to the left a bit, and this one over to the left a bit, you get an equal system. So if you're going positive and minus on your A to D converter, it becomes important. If you're just going positive, then you have the option to move this decision staircase over a bit. Or what I should say is pick a converter that has that decision staircase in that position, because it's not something you can change at a whim. You've got to pick the right one. The quantization error is the same in both cases, whatever goes on, because this width here is the maximum quantization error that can occur, and it's usually still Q over here, but it actually goes either side of the red line, so you get Q over 2, or plus or minus Q over 2. So as it says here, this type of construction is commonly used for converters that go positive and negative, as it gives symmetry around 0, and this one can be used for ones that only go in the positive direction. Doesn't really make a lot of difference in terms of quantization noise. The width here, Q, between levels is the same for the input signal that's coming in, but it's more convenient to define it as Q over 2 in this case, and we have maximum quantization error going between minus Q over 2 and plus Q over 2, which is still Q if you take the difference. So you can see there's some subtlety in the differences going forward, and this is just explaining that in a bit more detail here. It's just Q over 2. But the more bits we have, the better the resolution, and the lower the quantization noise as well, because this width gets less. But it is quantization noise that is the thing that's going to be of interest to us going forward. Okay, so an example. An analog signal in the range 0 to 10 volts is to be converted into an 8-bit digital signal. What's its resolution? What's the digital representation of input signal of 6 volts and say 6.2 volts? What is the error made for the quantization of 6.2 volts in absolute terms and a percentage of the input, and as a percentage of the full scale? And what is the max quantization error of this system? So there's lots of questions that can be asked about this on a fairly limited amount of information that we've got. And in fact, we don't actually have enough information to make a proper decision, so we have to make some assumptions. So we'll assume a sampler that is not offset by half a LSB. Thus the resolution from the previous slides is given as Vref over 2 to the n. And in this case, if we read the question, we're given a maximum voltage, not Vref. So if we're going to be completely accurate about this, we have to say the resolution is given to us by Vin max over 2 to the n minus 1, because we want to get the value of the LSB to get the resolution out. And then we've got the maximum value of the signal that what we're expected to deal with in this system. And so we put the numbers in. We've got V in max is 10, and we've got n equals 8 because it's told us that in the question. Put into the equation for this here, and we end up with a resolution of 39.22 millivolts. So that's the minimum change in signal that you need to make the converter change its output by 1. And we note then that Vref if it wanted to know what VREF was, it needed to be higher than this by the value of 1 LSB. So we need to add 39.22 millivolts to our 10 volts to get this working properly. So we're starting to deal with some quite accurate numbers now, if we want to be fully accurate about the whole thing. And then the other part of the question would be, what's the digital representation of an input signal of 6 volts and 6.2 volts? So we have to compare the voltage with each value of the most significant bit, and if it's higher, subtract the voltage and set the bit. So this is a sort of a successive approximation approach. So we've got 6 volts. The value of the smallest bit is 39.22 millivolts. The next, if we move along in terms of bits multiplied by power of 2, the next one is worth 78, and then that will double, and that will double, and that will double, and so on. So to get the value of the most significant bit that's valid, we would say, well, we take our 6 volts. The value of the highest number of bits is 5.01. 5.01 is less than 6, so we can subtract that, set the bit. That leaves us with a bit left over, 98 millivolts or so. Then we have to just compare it with these to see which is the smaller. This is the most small one, so we got 98 take away 62 millivolts, set that bit, and so on, follow it through. If you do that, you end up with a value of 153 in 8-bit representation for our value of 6 volts, and 6.2 is 158. There are other ways of doing this. We could just work out how many of the smallest values fit into 6 volts. So if we know it's 39.22 millivolts, how many times does this divide into 6 volts? 153, which then turns into the same thing in binary. And there are other ways of looking at it as well. You can also do it by hand, which is the same thing as we just did up here, really. The interesting bit is when we start to get close to a boundary, because when it's close to a boundary, even just sort of noise and temperature changes might mean that we actually out by a bit, because 152.98 is pretty close to 153. But if any of these values are slightly out, this might click over to 152, or even, you know, be the wrong side of 152, be 153. So it starts to become, this is where the quantization noise starts to become an issue. So you can run through this in your own time, because we're running out of time now, and just work out what the various errors would be. And you can see that it's relatively straightforward to work out what's the maximum error you can get, and quite quickly it shows you how to work this through and get an appreciation of what's going on. So if we use a symmetric converter, then things would just be offset by half an LSB in this direction, so the average errors will still be the same, but the specific errors for particular values will be different. So just be aware that this can happen. I say in practice doesn't really make a lot of difference. And then once you've got the values in, these are all, you know, whatever comes out the A to D converter is going to be an integer number, and that instantly introduces this quantization error. If you then, you know, just multiply that by the value of the LSB, that tells you what the value of voltage the digital system thinks it is. So in this case, digital systems thinks it's 6.196 volts. We know it was 6.2 going in. We've got an error there of 4 millivolts or so. Percentage error of 6.2 volts is easy enough to work out. 4 volts of 6.2, 4 millivolts over 6.2, 0.06%. And a percentage of full scale, we know the full scale was 10 volts. We know the error is 4 millivolts, so we can work out the error as being 0.04%. And what is the max quantization error? Max quantization error, same as the LSB, which is 39.21, or if you looked at my earlier calculations, 39.22 millivolts. At some point you've just got to accept there's going to be a slight difference somewhere. There's always differences. Right. We will just quickly cover this slide. Quantization noise is something that we need to be aware of, so I'll just quickly do this. So if we look at the probability of error of a random signal, then the error is going to be constant over all these inputs. It's equally likely to be any of these quantization errors. So this is what the probability graph looks like. And the average error, that's going to be 0 in the middle. but we can calculate the mean square value of this, and we also note that because this is a probability of error, the area under this curve must be equal to 1. And we know that the width across here is q, so the probability error is 1 over q. The height of this curve is 1 over q. So to get the RMS value of this, we just have to multiply the square of the quantization noise E, which is 1 over q, by its probability to give us the square of the mean, and so we just have to integrate across this whole area, and this allows us to work out the square, the RMS value of the quantization noise, and it always comes out to q squared over 12. So this is a good number to have learned, and it's just some basic integration of a nice square probability function. Take the square root of this gives us the RMS of the quantization noise, or quantization voltage, and this is the fundamental limit of noise in your quantization system. This is not analog noise, this is digital noise. So q over root 12 is something that we're going to be interested in as a number, and q is obviously the quantization error. And this allows us to calculate a signal to quantization noise then, because the peak value of the full scale sine wave, i.e. it's peak to peak, covers the whole range of the ADC, so we're assuming that we're putting the maximum signal we can into this A to D converter. That's going to be given by 2n, where n is the number of bits, and then we've got the quantization error, and that's half of it. So we end up with the voltage of the signal, RMS voltage of the input signal in terms of quantization error anyway, is 2 to the n over q over 2 to the root 2. And so to get the signal to quantization noise ratio, we just need to take this value and divide it by the q squared over 12 that we got from the previous slide, and that gives us this value here, and this is often presented in decibel form, and if you convert these, you've got 1.5 here, so you do 10 log 1.5, multiplies become 10, it adds in the 10 world, so we've got 10 log 2 to the n, and then that's a constant, so you can just work that out. Simplify this, so 2n comes outside, gives us 20n, 10 log 2, that all boils down to 6.02n plus 1.76 dBs. So the signal to quantization noise of any digital system is entirely defined by n, the number of bits of resolution that you have, by this formula here, and this is the best signal to noise you'll get, because this is for a maximum signal coming in. So the more bits you have, the better the signal to noise ratio you're going to get. And for a 16-bit system, you can work this through. The signal to quantization noise ratio becomes 98 dBs, and if you're not familiar with dB levels, then you'll get quite familiar with it. 98 is a big number, so if you un-dB that, it'd be huge. So not really worrying about, and that's the implication you get, because a 16-bit system is actually a very high resolution system, good enough for 99% of all systems you're ever going to deal with. People try and go higher, but there's not a lot of point really, because the noise in this system is so low that it's going to be dwarfed by any analog noise that you've got in your system, which is much more difficult to get rid of at low levels. Right, so that was a count up to signal to quantization noise ratio. This equation is quite an important equation going forward. It's a good thing for exams, for example, so keep an eye on that, and then we'll carry on looking at A to D converters in the next lecture.